Hello everyone, I'm Atanu Shubham Rai, Research Assistant at the Robotics and Automation Research Lab at Jiangsu University and Science and Technology. I'm presenting our work titled Path Planning for Automated Guided Vehicles, Balancing Computational Efficiency and Optimality, conducted with Dr. Ata Jahangir Moshayedi and our collaborators. Automated guided vehicles or AGVs play a vital role in industrial automation, logistics, and modern smart mobility systems. Yet, efficient path planning remains a key challenge, particularly for electric AGVs that must manage both energy and time efficiently. Traditional algorithms such as Dijkstra, Floyd Warshall, or DFS perform well in static environments, but they often overlook energy usage and the trade-off between cost and station coverage. In short, existing research tends to focus on either optimal routes or fast computation, rarely both. Our goal is to find a balance, algorithms that are not only computationally efficient but also energy aware for EV-based AGVs. To achieve this, we evaluated 11 classical algorithms, including Dijkstra, DFS, Floyd Warshall, Prim's MST, and binary search, using an Ackermann steered electric AGV. Two routing strategies has been implemented. By station, where the AGV plans globally between charging stations. By edge, where it moves along predefined edges or waypoints. We assess their performance using conventional metrics like runtime, distance, cost, speed, and station coverage. But we also introduced a new evaluation measure, the Energy Consumption Score, or ECS, which combines computational and operational costs into a single efficiency metric. Previous studies demonstrate that classical algorithms still perform strongly when properly tuned. For example, Wang and Fuzley refined Dijkstra's algorithm for smoother grid navigation, while Alshamre adapted it for ultrasonic-based mobile robots. Hamed and Zhang optimized AGV scheduling and MST efficiency, and Li used Floyd Warshall to validate optimized routing through simulation. These works motivated us to revisit these classical approaches under modern EV-based conditions to see how they truly perform when energy and computation are both considered. Despite these successes, most existing research lacks energy-aware metrics and comparative analysis under EV constraints. We address this by testing 11 classical algorithms across three families: exhaustive, greedy, and dynamic programming. Exhaustive has TSP, binary search, and DFS. Greedy has Dijkstra's Prim's MST, Kruskal's MST, Josephus, Tournament, and Kedin's MSS. Dynamic programming has Floyd Warshall and Knapsack 01. As you can see in this figure, all are classified accordingly. Each algorithm was adapted for EV-based AGV navigation system and tested under both by-station and by-edge routing. In the by-station mode, routes are dynamically optimized using a cost matrix between stations. In the by-edge mode, travel occurs over predefined segments between waypoints, emphasizing consistency and modularity. The classification of each algorithm based on by-station and by-edge is defined as the figure shows. For the robot movement, we have chosen the following algorithm. Basically, the robot calculates the angle and the distance from its target that has been calculated from the different algorithms and then moves towards the directed point by adjusting its error repeatedly. For the simulation, all algorithms were implemented in Copilot Sim version 4.9. Our environment contains 6 charging stations, or 6 stations, you can say, connected in a weighted graph. The Ackermann steered AGV was equipped with realistic kinematics and sensors, as we will see later on. Each algorithm was embedded directly into the robot's control loop to execute paths in simulation and measure true computational and energy performance. Here is a figure on how the 6 stations are managed. On the left, you will see one graph that connects each of the station and their distance as their edge weight. And on the right side, the actual simulation ground that has been constructed in CopiliaSim. For the performance matrix, we evaluate standard parameters such as execution time, speed, distance, cost, terminal stations visited, time complexity, space complexity, and also Hamiltonian path. Furthermore, we proposed a new metric, which is ECS, that stands for Energy Consumption Score. The Energy Consumption Score combines all of these standard parameters into one weighted measure. Basically, ECS equals 0.25 times time, 0.10 times speed, and so on and so forth from this equation. Basically, lower ECS means higher efficiency. We calculated ECS based on the influence of each of the standard parameters on our energy consumption. The results were quite revealing. Floyd Warshall achieved the shortest execution time, about 154 seconds, and the least traveled distance, roughly 21 units. But it only covered one station. TSP and Prim's MST had moderate times, around 688 seconds, yet achieved full 6-station coverage. At the opposite end, Josephus and Kruskal's MST were the slowest and least efficient, exceeding 2900 seconds with long paths. In terms of ECS, Floyd Warshall scored lowest as well, meaning most energy efficient, followed by Dijkstra and TSP. Prim's MST and Keren's MSS offer moderate ECS, while Josephus and Kruskal had the highest, reflecting high computation and energy waste. Here is a summary of all the different results that we have seen so far. As you can see, for the ECS, Floyd Warshall achieved the lowest. Lower ECS reflects better battery optimization. Floyd Warshall obviously exceeds in all of that. However, Josephus and Kruskal MST were inefficient because of the long computation and the poor routing. Greedy Dijkstra and Prim's MST balanced speed, route quality, and energy use. TSP, however, maximizes station coverage, but also it comes at a high computational cost. This is another slide of the entire summary of the results. From these experiments, several trade-offs emerge. Floyd Warshall is best for minimizing cost but poor in station coverage. TSP and Prim's MST excel in coverage but are computationally demanding. Dijkstra delivers a strong middle ground, efficient, balanced, and practical for real-time use. Between routing modes, by station offers better global optimization, while by edge is modular and easier to scale, but less efficient overall. These findings confirm that even traditional algorithms can yield competitive results when energy matrix are integrated. We have a short demo on binary search being run on CopiliaSim. As you will see, the algorithm already decided which path it should take, and then it's covering them one by one. All the data and the video footage are recorded for further analysis. In this section, we have a comparison video among all the algorithms that we used, and they are classified here according to the 3 approaches that were used for implementation and also the two routing strategies that we used. As we can see, all the vehicles in all the different algorithms are off to the races. And here, Dijkstra finished fast, and then Prim's MST, then Kruskal's MST, and finally, Josephus's algorithm is just taking its sweet time. And finally, Josephus finishes. In the second section, we have Tournament's algorithm, MSS, Floyd Warshall, and knapsack. As you can see, Floyd Warshall finished first, followed by Cadence MSS, knapsack, and finally, Tournament's algorithm. For the third section, we have binary search, DFS, and traveling salesman or TSP working to win this race. And TSP finishes first, binary and DFS follows soon after. To conclude, classical algorithms remain surprisingly effective for static, predictable AGV environments. Our proposed energy consumption score provides a unified benchmark to compare them both under computational and operational dimensions. Depending on system priorities, for cost efficiency, use Floyd Warshall, for coverage, choose TSP or Prim's MST, and for balanced performance, Dijkstra remains the most versatile option. Thank you for your attention. For any questions or collaborations, feel free to contact me at the following email. Thank you.